Okay, so this is the second video for the chemistry series, and we're looking now at isotope stability and radioactive decay. So, as we were discussing before, some isotopes are unstable. There's sort of three reasons why they might be unstable. So, too many neutrons, so the proton to neutron ratio is off. Again, too few neutrons, the proton to neutron ratio is off, but in the other way. And if a isotope or an atom is too large overall, it will also decay. But they'll decay in three different ways. So, first of all, if there are too many neutrons, the proton to neutron ratio is too high. So, greater than 1.1 to 1.5 is generally where something will undergo what's called beta decay. So we talked about this a bit before in the context of tritium. So you have this atom, it's arbitrary, and it's got a whole bunch of neutrons, and you want one to become a proton. So conservation of charge spits out an electron, becomes a neutron. Make sense? The second case, too few neutrons. That's where you get what's called positron emission. So you have all these protons around, only a few neutrons. You can turn a proton into a neutron by emitting what's called a positron. It's the antimatter equivalent to an electron, and that just zips away and usually annihilates somewhere else, and you get lower proton to neutron ratio. Higher proton to neutron ratio. And the last case is where the atom is too large. So this happens for any element with an atomic mass greater than 82. So any element after lead on the periodic table. It starts with bismuth and goes up to like plutonium, uranium, einsteinium, yttrium, quadium, and all of those fun ones. So here we have a huge atom. It wants to get smaller, so it actually ejects a helium nucleus, 42He, so it has 2 protons and 2 neutrons, and the mass number goes down by 4 and the atomic number goes by 4. Just to mention, if you don't know, if you write, for example, potassium 4019, this is the mass number. So that's the number of protons and neutrons added together. So it's like the atomic mass, and this is the atomic number. So that's what element it is. Number 19 is potassium, I'm pretty sure. Yep, I'm right. So there are a few other types of nuclear decay. A couple of the rare ones are neutron emission. So in some cases, like with helium-5, it has an extra neutron in its nucleus, but it doesn't decay down through beta decay. It actually just kicks the neutron out of the nucleus and it emits a neutron. So that one's pretty straightforward. And this type of nuclear decay equation you should also be familiar with. So 5-2He, so it has an extra neutron instead of 4 as the mass number, it's got 5. Decays down to 4-2 helium plus 10N, which is a neutron. So 1 but no charge. So that's that. And here you have electron capture, which is another sort of rare type of radioactive decay. You have potassium 40 plus an electron. It's capturing. You can write an electron also as -0, -1. So it has a negative charge but 0 atomic mass effectively, and that's becoming argon 40. So it's capturing that electron to raise the neutron to proton ratio. One more to mention is gamma decay. So gamma decay, and you can write the Greek letter gamma, which I'm never very good at writing. What happens here is that you might have a excited nucleus, and you put a star to say it's excited. Often this happens after other radioactive decay. So you've beta decayed, then you've got your subatomic particles in an excited state. So when that happens, it goes down to an unexcited state. No change in the element or the isotope happens at all, but you release a gamma particle, which is a high energy photon. So it's basically just high energy light, but we mention it because, first of all, it's mentioned a lot in literature, and it is part of the safety side of radioactivity, because gamma radiation is very penetrating. Anyway, so that's it for types of radioactive decay.